All right, welcome everyone. So today we're going to be talking about the Web3 data zoo and a quick demo about how Chainalysis kind of navigates that. So today I'm going to be running through a product demo of the Datalore collaborative data science platform, which Chainalysis leverages throughout many of our teams, from our data science teams to our research teams, to collaborate on, as you'd imagine, data science. So most of you are maybe familiar with Jupyter notebooks. That's probably how a lot of data analysis starts. Well, the JetBrains Datalore platform is kind of the next generation for that. It allows collaborative editing like Google Docs and a lot more, which I'll demo some of. So what I'm going to be showing you today is actually going to be a presentation that I gave to some degree to Inside Chainalysis about a year ago, demonstrating how we can actually query and analyze Web3 data given what was happening at the time, which was the NFT hype. So what is Web3? Well, some of you might have heard about this term recently, especially, let's say, Q1 2022. Let's mark that as the hype with this chart. So recently, crypto went through one of its classic boom and bust cycles, and NFTs were somewhat to the center of it. The narrative this time was heavily focused around the idea of Web3, which is the idea of democratized, decentralized data stores. So the idea is Web3 data is available for everyone to analyze, compared to Web2 data companies that end up building data and then selling that information. Web3 data is available to all through the Web3 data sources. So recently, as I alluded to, crypto went through a cycle with NFTs at the center. Here we can see that NFT sales with buyers and sellers was steadily increasing, and around Q1 of 2022 was the recent peak that we saw. And since then, as most have probably seen through the prices and so on, the industry has actually deflated and entered more of a bust scenario or a bear scenario now. So based on this, we know that the hype grew a lot recently. So one of the more interesting things that occurred around this hype cycle was one of the most expensive sales of an NFT at the time. So Beeple auctioned the first 5,000 days, which was a purely digital NFT, through the Christie's auction site. And it got bids all the way up to approximately $70 million. So that places Beeple within the top 3 most valuable living artists. So clearly there's a lot of money moving in this, and the value of this system is growing. So what we want to do now is actually see what is this NFT sale, and how would we interact with it on the blockchain, or sorry, in Web3 data stores, and how would we actually get this data? So over here is the actual auction listing on the Christie's website. You can see Beeple, the first 5,000 days, every day's the first 5,000 days, the price realized, and a bunch of meta information. So this is actually where we would get our core blockchain identifiers. So in this case, what we want is really the smart contract address and the token ID. So these are our 2 main identifiers to go look up, like, what is this NFT and what data is stored within it. So let's copy these into our live coding cells. So the address we're interested in is this one right here, and the NFT ID, or let's call it token ID, is the one we just saw over there as well. So now we have the targets of the 2 things we want to look up: the contract address and the given identifier within that contract address. And now our task is to look up this metadata and verify that it actually contains the information that we believe it does. So a quick background into myself. So I'm Surya Rastogi. I am a senior staff data scientist at Chainalysis, and I've been doing blockchain research for over 7 years. For the past 5 years at Chainalysis, I've built various things like data pipelines for blockchain acquisition, and enhanced our labeling systems, which is branded as clustering. Most recently, I've been working in our research division to look into some of these more deeper level Web3 activities. So, what is Web3? Kind of as I mentioned before, the idea is that it's a democratized, distributed data source that's spread across the internet. So these are distributed protocols with participating nodes around the network. And these all comprise together the distributed data store that we will be talking about. So one thing to know that's different is, as you imagine, if there are distributed nodes all around the network, all reaching consensus, where would you query your data from? And that's kind of one of the issues. There's no central place to query your data. There's no canonical data source because there is no one person in charge. Collectively, the network is in charge of the data that's uploaded, maintained. So to query this data, we actually have to query a node. So we will demonstrate that a bit later, querying directly a Web3 node in order to get data. And we'll do this for both the EVM blockchain as well as the IPFS, InterPlanetary File System, which is used to store data, store file-like data. So yeah, as I mentioned, the two protocols we are mainly going to be looking at is the Ethereum blockchain and the Interplanetary File System, known as IPFS. So I'm not going to go far into the philosophy behind blockchains, but one of the ideas behind the blockchain is to provide a global data structure that the whole world has consensus and ability to influence the consensus of. Bitcoin started with the idea of having a public ledger where everyone can make transactions that move their value that they store the cryptographic information for. Ethereum wanted to go one step beyond that. So in around 2015, when the network launched, Ethereum's core idea was to provide a generic computing service on which a lot of these decentralized apps could be built on top of. So the idea was to make an arbitrary programming language with the Ethereum virtual machine that could execute arbitrary code instead of having a purpose-built distributed system like Bitcoin, which is purpose-built for value transfer, or others at the time like Namecoin and so on, which were particularly built for a given use case. So the way Ethereum does this is it has, as I mentioned before, this Ethereum virtual machine, and there are a couple of languages that compile down into the Ethereum virtual machine. The one that we're going to be looking at today is called Solidity, and it is one of the most popular smart contract languages on Ethereum. It's also used by other what are called Ethereum virtual machine EVM chains, which now there are quite a few. There's Matic and a couple of others, all running the same base level code. So these interfaces, as they're called, ERC-721, is actually just a code contract that's defined here. Just as you'd read any other code, you can see kind of the functions that are provided to you, as well as this is a blockchain-specific construct called events, which is another data structure that you could query. So here we kind of have the spec for what's known as the ERC-721 standard. The ERC-721 standard was set so that there would be a singular way to view non-fungible token transfer movements, and the core idea really is you have the from, the to, and then the ID of the good being moved. So at its core, that's effectively the things we need to know, is the token ID for the given non-fungible token, and then we'll have a bunch of meta information like from and to, depending on the different calls we perform. So one additional interface that's described in this is the ERC-721 metadata interface. And this interface is kind of what it sounds like. It stores the metadata associated with NFTs. So here, the token URI function is the one that we actually want to call on the Ethereum blockchain. We want to know what is the token metadata stored in the Ethereum blockchain related to the token ID that we chose above. Actually, one thing I forgot to do in the cell above is some imports. So let me quickly do that. One thing we do need to leverage, which I'll show a bit later, is we do have to install the PySha library just to use some hashing functions, which will come in a bit later. I'm just running that now so that I can have that done. So let me get the imports in place. So most of the data is serialized as JSON, so probably libraries most of you, if you're familiar with Python, are already familiar with. And then we're going to use the very base level request library, which lets us do HTML requests. And lastly, we're going to leverage some IPython internal libraries to show the image all in one place. So those are our imports. And now what we want to do is figure out, as I just mentioned, what is the function we want to call. So the function signature to call is equal to what we just mentioned there. It is this token URI function. So one thing here is if you click the link I have above, it'll take you to the spec where it goes through some of this in more detail. But effectively, you have to truncate this to just its type signature. So this is its type signature, which is token URI, and the input it expects is this very large uint. So you might be wondering, what is this ridiculously large uint, a uint 256? Well, that's actually the base word size of Ethereum. So even if you have a Boolean value that's a bit, it's going to take up this amount of data on chain unless it's packed with other bits, because this is the minimum word size available on the Ethereum virtual machine. For those who don't know what that is, it'll come back maybe a little later, but it's more compiler language stuff, which relates to what we're going to do next. So this is now the function we want to call, and what we now need to do is some cryptographic forward hashing. So here we have the Solidity Spec. This is kind of for what I was alluding to before, people who are more interested in how the language is actually compiled forward. For others, you can just trust what I'm doing here because it'll look approximately right. But what we're doing is we're effectively using the SHA-3 Keccak 256 algorithm, which is what the Ethereum blockchain is based on. Then I need to update some. Here I'm actually just copying code that I've written below because it's a little non-trivial. But effectively what I'm doing is, that's strange. Okay. Code. So also it uses ASCII encoding, which we will need on the reverse side when we decode the return data. And now this is something strange, which is if we read the spec above that we have, the Solidity ABI spec, it'll tell us that we actually truncate the starting 4 bytes. So what we want actually is the hex digest, but only the first 4 bytes, which would translate to 8 string characters. So this is the 4 bytes call for it. Oh. If you're familiar with Ethereum, you might know about the 4 bytes database, and this is how you actually get to that point. But for those who don't know, that's unrelated. And now we need to do the same, which is we have to serialize our parameter. So the parameter is the token ID we just talked about. Oh. Yeah, so there's the parameter. But as I mentioned, the issue that before was we have these ridiculous word sizes. So what we actually need to do is we need to pad it so that it fits up the very large word size that we mentioned before. So padded parameter equals this. This is a little Python hacky, but I'm basically removing the 0x prefix that comes when you stringify it, and then adding a lot of zeros to the start. And that's, yeah, it's, as I mentioned, 256-bit words. That way, this is effectively the parameter that we will have to send. So it's kind of long. Okay, so Json Rpc, that's just another, as I mentioned before, we're not going to use SQL. We're going to use Json Rpc to query the data. I will very quickly write that out. Sorry. So one thing to mention is we need to know what we're actually querying. So here we're going to take, let's take the Cloudflare URI. So this is the node that I was mentioning before. Sorry. Okay, I am noticing I'm may be running a little low on time, so I'm going to copy and paste that cell because it's a little complicated from the preset one. So I will go over this right now, but I'm just copy and pasting it for the sake of not typing. So what we're doing here is a very basic Json Rpc request. So we have the RPC URL we just looked up on this Ethereum nodes website. Each of these is a participating node in the network. So you can choose whichever one of these you want to query the data from. And that's important because this shows that it's truly a distributed data source. There's no one canonical copy. All of these are equally valid canonical copies. Some of these have different uptime and downtime properties, which is why you may want to register for a key. I'm currently using the Cloudflare one because it doesn't require any key. So what we're doing here is we're constructing this Json Rpc call. So we're using the Json Rpc 2.0 protocol, where the method key that we're sending is eth_call. So what this is saying is I want to run this function in the Ethereum virtual machine, and everything after the call is effectively the function identifier and the padded parameters. So as you can see, I'm sending this to the address, which is the contract address we looked at the start, listed on the Christie's website, and I'm sending the data, call the function we described up here, token URI, call this token URI function with this padded parameter, which is the one we mentioned before, this 40,913. So this is all the data we are serializing and are now going to send to effectively the Ethereum blockchain node. It will return with data, and as I mentioned before, we need to decode that data in some way. So it is using ASCII, so as we encoded the hash forward into ASCII, we're going to decode the return data back from ASCII, and we're actually going to remove the first chunk. So if you look here, this is that magic 256 number, which comes from the word size, but we're effectively moving the first chunk because when you return a list, the first chunk is usually either the list of the length of the list, or null, or like some other things for different data types, but it's null when it's an unbounded list, which is what it is in this scenario. And similarly, it has to be padded with null bits at the end, so this replace is removing the null bits at the end. So when we run this, we're actually going to be making this call and seeing what we get back. So we get this Q string back. Actually, that's a lie. I'm going to show you the raw data that we get back just so you can see some of it. So you can see it has that strange null bits at the end. That's because of missing padding. And then we can see it's IPFS is the protocol. It's a URI, as some of you might be familiar with URIs. IPFS is the protocol. And then this is the target hash that you can resolve on IPFS. So now that we have the IPFS hash, we should go look it up in the IPFS database. So the InterPlanetary File System. It is not a blockchain, but it is often considered under distributed ledger technology because it is a decentralized data store with similar consensus mechanism, not really consensus mechanism, but similar routing and data indexing mechanisms, let's say. So you might wonder, why not store everything on the Ethereum virtual machine? Like, if we have some of our data there, like this metadata and this hash pointing elsewhere, why not store everything? And some NFTs actually do store everything if they have small enough amount of data. But the issue is you're paying effectively for every piece of data you're having on the EVM, so it's very expensive. It's kind of like saying, well, why don't you store your hard drive in RAM? And it's like, well, if you had giant RAM sticks, you could actually do that. You could do memory map files, but that's very expensive. So along those same lines, IPFS is kind of a cheaper binary store to the more expensive consensus-based stores that are in the EVM. So one thing to highlight, though, is IPFS data is not transactional, which I won't really get into here, but it means the data could be missing at some point, or removed, or not hosted, and those get into a bunch of other incentivization issues. So the same way that we looked at with Ethereum, we can look at the Web3 nodes that are available for us. So this is a list maintained by the IPFS org of all the available gateways. So these gateways we can use effectively to see what data is stored in IPFS. So let's choose one out of those. And I think we'll go with the official IPFS one. So gateway URI. So now we're just making a simple GET request to the gateway URI. And then slash, IPFS slash, and then we want to put the IPFS hash itself. So the hash we got up here, we're going to put that into the IPFS data. And then we'll just kind of print out the JSON of it. So there we go. So here is the metadata being stored on the IPFS system. So we can see the title of the work here is every day is the first 5,000 days. There's an image URL, which is what we'll take a look into next. There's also a description. So the artist has actually uploaded their own description of what they're doing. So every day from May 1st, 2007 to January 7th, 2021. Yeah, there's some profanity there, but this is every piece of work they did for those days. Now let's actually look it up. So as we saw, there is there's this image URL field. Which is a regular link. So we can follow this. One thing you might notice though is it actually looks a lot like an IPFS link, right? And that's because it actually is, but this is just the gateway that's being hosted by Makerspace. So Makerspace is hosting this through their own IPFS node and making it available for faster speeds, but effectively I can take this same queue hash and request it from any of the other providers the same way we were looking at before. Like, let's say we wanted to try it here. This could go badly because I feel like live coding doesn't always go well. But here, let's try dropping that link that we just saw and seeing what we get. So we get the same thing. We can say that multiple different nodes all agree that this image is what is being pointed at across the distributed net. So we actually know that we verified this is the image that canonically is pointed to by this hash that is on the blockchain. And we can query any iteration of IPFS or any iteration of Ethereum nodes running on the same, any regular Ethereum nodes. And we can verify any of the data that's behind these NFTs. Now, one issue here is I actually showed you that with this Q hash, it is actually stored on Web3 through IPFS. One of the issues is there's nothing preventing anyone from just storing the metadata, like here, on IPFS, but then linking to a centralized website, like linking to like suryarastogi.com/an image. And it's like, well, then you're just pointing to whoever owns that DNS's thing. And it's like, I might choose not to renew that domain and someone else takes it over and then put something else there. And it's like, that's not actually decentralized storage. That's not Web3. That's just actually Web 2 with links from Web 3 to Web 2. Whereas the things that I just showed you, where you can verify the data's on IPFS and verify the data's on the Ethereum blockchain, those are ways to know that it's truly decentralized and distributed, rather than just pointing at a centralized location. So yeah, I hope you all learned some nuances about querying Web3 data, and I hope you found this interesting, and thanks for all of your time. Also, if you're interested, feel free to scan this link, scan this QR code, and it should take you to some of the JetBrains marketing materials related to this report. So if you want to copy and paste any of this code, try it out yourself, even make a copy of the notebook on the Datalore platform, feel free. And yeah, we're here, JetBrains is here in a booth, so go talk to them. Thanks.